Hello, my darlings. Okay, so today we're going to start talking about modeling and solving differentiable equations. Up to this point in your mathematical career, usually when we solve an equation, we get a numerical value as an answer. Now we're going to solve a certain type of equation called a differential equation, where our solution is actually a function. So a differential equation is any equation that involves one or more derivatives of a function. And these equations describe relationships that involves rates of change, because that's what a derivative is, and differential comes from derivative. So consider the following statement. The population P of your state is growing, that's how you know it's a rate, at an instantaneous rate, that's how you know it's a derivative, of 3% of the population per year. So the derivative of the population, that's dp dt, is 3% of the population. We write 3% as 0.03 times p for the population. This whole equation is what we call a differential equation. dp dt equals 0.03p. So now let's try to write some ourselves. So we're going to write a differential equation that describes each relationship stated below. Okay, so Alex and Tina have a new Maine Coon kitten named King Robert. Robert is gaining weight, W. Now, if it's gaining weight, we know the derivative is positive at a rate, so we know that the rate of change of the weight, dw dt, is inversely proportional to. So inversely proportional means we're going to have a constant k over his age t in months, and that's how we would write that. Okay, if it's proportional to, it would be dw dt equals kt. Inversely proportional to is dw dt equals k over t. Now let's try another one. Your cup of Starbright's peppermint coffee is cooling, so it's a negative rate, at a rate that is proportional to the difference between the room temperature TR and the current temperature T of the coffee. So our coffee temperature, that's T, is cooling at a rate. So the rate of change of the temperature of our coffee over time is cooling, so it's negative, at a rate that is proportional, so I need a constant times the difference between the room temperature and the current temperature. Well, the coffee is probably hotter, so T minus TR, and there's our differential equation. Awesome. Okay, read the problem through first, then go step by step and translate a little bit at a time. Now we're going to verify solutions for differential equations also before we start solving them. Okay, now remember, the general solution of a first order means it has one derivative of a first order differential equation represents a family of curves. Remember when we did antiderivatives, we had a plus c? That gave us a family of functions because the constants could be different. Well, again, same thing with differential equations. We will have a family of curves, okay? Now let's look at some different ways we can represent these. Now it's important to remember that when we're looking at a differential equation, y is the same thing as f of x. It all depends on whether you're using function notation, Leibniz notation, or if you're using the y's in the differential equation, okay? That also means that our f prime of x can be written as y prime or dy dx, right? dy dx is the Leibniz notation. And that means that our second derivative of f of x could be written as y double prime or d squared y over dx squared, the derivative twice of y with respect to x twice, okay? These three equations represent the same differential equation. They are all three different ways to write the same differential equation. Okay, so to see how there's a whole class of functions or a family of functions that can satisfy this particular differential equation, let's look at the family of function y equals a times e to the bx. So in the next example, we're going to show how two of these, right, they're both in the form y equals a number times e raised to a number times x. In the first one, a is 2, b is 1. In the second one, a is 1, b is negative 4. And this is the differential equation that we had in the chart on the previous page. And we're going to show that both of these y functions work in the differential equation. So let's start with y equals 2e to the x. Now I noticed in my differential equation I need y, I also need y prime, and I need y double prime. Okay, so let's take y, and we know what y is. Now I need y prime, that's the derivative. Well, we keep the 2, and the derivative of e to the x is still e to the x. Now I need the second derivative. We keep the 2, and the derivative of e to the x is still e to the x. So notice the function, the first and the second derivative are all the same. Now we're going to take this differential equation, 3y prime plus y double prime equals 4y, and we're going to substitute in what we know. We have 3 times, now what was y prime? 2e to the x plus y double prime is 2e to the x equals 4 times y is 2e to the x. Now if we do some simplifying, we have 6e to the x plus 2e to the x equals 4 times 2 is 8e to the x, and notice 6e to the x is plus 2e to the x is equals 8e to the x. This is true. Awesome. Okay, now let's look at the second solution and see if it works. Y equals e to the negative 4x. And again, we're going to need to find the first derivative, but this time the derivative of e to the negative 4x is e to the negative 4x times the derivative of the exponent negative 4. Okay, and we need to find the second derivative, which is e to the negative 4x. Now we have a negative 4, and we have to multiply by the derivative of that exponent, so that's another negative 4. So negative 4 times negative 4 is a positive 16. Now we have our function and our first two derivatives. So we're going to write our differential equation, 3y prime plus y double prime equals 4y. We're going to make our substitutions. 3 times y prime is negative 4 e to the negative 4x, close it, plus y double prime is 16 e to the negative 4x equals 4 times y is e to the negative 4x. Now we're going to do some work here. 3 times negative 4 is negative 12 e to the negative 4x plus 16 e to the negative 4x. And then we have 4e to the negative 4x. And notice negative 12 plus 16, that is indeed 4e to the negative 4x. These are the same. We know this is true. This is a solution. So if you're asked to verify, all you have to do is find the correct number of derivatives that you need for your differential equation and substitute. It's just like checking when you solved an equation in algebra. Now we're ready to start solving a differential equation. So here we have the differential equation, dy dx equals negative x over y, and we have the initial condition that y of 0 equals 2. Okay, so I'm going to start by writing my differential equation, dy dx equals negative x over y. Now the first step is to separate the variables to either side of the equal sign. So in other words, get all the x's on one side and all the y's on the other. So I need to move this y to the other side and this dx to the other side. So in order to do that, I'm going to multiply by y and I'm going to multiply by dx. Now I have the variables on the correct sides. Next step, we are going to integrate both sides. Okay, so I can integrate one side as long as I integrate the other side. All right, now the antiderivative of y is y squared over 2. Now I know there's a constant, but hold that thought for a second. Equals negative, and the antiderivative of x is x squared over 2. Now I get a constant on this side. If I have a constant on the left and a constant on the right, I can bring them all to one side and just have plus c. I suggest you do that because you don't want to have to deal with two c's. This gives you a constant, and then you only have one to solve for, and if it's on the side with the x's, it'll be easier to solve for y in the end. Now, that said, if this is, let's say this is C1, you can, I know some of you hate fractions, okay? So you can, and I'm going to do this both ways. you can clear the fraction. How do we clear the fraction? We would multiply both sides, every part, by that least common denominator 2, and we would have y squared equals negative x squared plus, now 2 times c1, that's 2 times c1, but that's a new constant, which I'm just going to call c2. That's a neat little trick, right? That's a little scary trick there. You'll get used to it. It's one we're going to use a lot. So don't worry, it'll get better. Now, let's get back to solving. Our next step is to use the initial condition to find our constant c. Now, on the left side it's c1, on the right side it's c2. And I don't care which way you do it, but I do want to show you both ways. Now, remember our initial condition was that y of 0 equals 2. So that means in this equation here, y is 2, so 2 squared is 4 over 2 equals negative x is 0 squared over 2 plus c1. Well, 4 divided by 2 is 2, and that means our constant is c1. Now on the other side, we would substitute in the same point, y of 0 equals 2, and when we substitute in, y is 2 squared is 4, negative x is 0 squared plus c2, and this time our constant is 4. So notice we have different constants. Is that okay? We shall see. We also have different equations, so it's probably okay. Now we're going to write the solution. Okay, so now to substitute the c value into our equations up here and then solve for y, or put it in standard form depending on what kind of function we have, or if it is a function, what kind of relation we have. So here we would have y squared over 2 equals negative x squared over 2 plus our constant is 2. Now we want to put this in standard form, so you know that trick I did earlier? We're going to multiply the least common denominators by 2, so we had to do it eventually anyway. This will give us y squared equals negative x squared plus 2 times 2 is 4. Now, I see the form. If I add the x squared plus y squared equals 4, I can see I have a circle with a center at 0, 0 and a radius of 2. Now on the other side, I had to substitute this into this equation, and I have y squared equals negative x squared plus 4, and all I have to do is add the x squared. So really, we have the same equation, and we're doing the same work. The key is whether we're multiplying by the 2 before we solve for c, or we're multiplying by the 2 after we find the c, okay? Now, I want to take our differential equation, and I want to put it in our TI calculator with our slope fields document. And then I want to graph our specific solutions to the slope field. Now remember, if we have x squared plus y squared equals 4, that's y squared equals 4 minus x squared, or y equals plus or minus the square root of 4 minus x squared. So in the calculator, we need f1 of x is the positive square root of 4 minus x squared, and f2 of x is the negative square root of 4 minus x squared. And we're going to go take a look at that on the slope field. So here we are, and we're going to define our g of xy, our differential equation dy dx, to be negative x over y. That's the same one we want. And we go to look at our graph. Notice this is a family of circles. Okay, you can see them, that it's a bunch of circles all centered at the origin. Now if I tab up, we can put our particular solution. We're going to control square root 4 minus x squared, arrow down, the negation of the square root of 4 minus x squared, and hit enter. And you can see how our circle goes right around those little tangent lines. And that's our particular solution amongst the family of solutions. Okay, I just want to do one more quick little differential equation. Notice this time we don't have an initial condition, so there's going to be a plus c. So our differential equation is dy dx equals the quantity 1 plus y squared times e to the x. Now, we're going to get everything with a y to one side and everything with an x to the other side. Now the key is your dy and your dx have to be on the top main line. They cannot stay in the denominator when we integrate. You cannot integrate 1 over dx. So the dx has to go to the right-hand side, and the dy has to stay on the left-hand side. So when I divide by 1 plus y squared, and I multiply by dx, there's my separation of variables. Now I'm going to integrate both sides. And now, do you remember your antiderivatives? The antiderivative of 1 over 1 plus y squared, that's tan inverse of y, equals the antiderivative of e to the x is e to the x plus a constant. And we have solved our differential equation. Okay, guys, we're going to stop here for now. I'll see you soon. Have a good one. Bye.